These presentations will describe strategies for analyzing quantitative diffusion tensor imaging data. It is not intended to be exhaustive, but describes a few representative approaches. First, we will review how we should think about interpreting DTI measurements. Just a quick review of the steps associated with DTI processing. We acquired a set of diffusion-weighted images on the MRI scanner. The diffusion tensor is then estimated by fitting a signal model to the raw diffusion-weighted images. The tensor diagonalization is then used to estimate the three eigenvalues of the diffusion tensor, which may then be used to estimate the mean diffusivity and fractional anisotropy. If you recall from earlier in the semester, we described the diffusion tensor model, how DTI data are acquired, processing steps, and the methods for diffusion tensor estimation, and several quantitative diffusion measures, several of which are depicted here. Common DTI measures include the fractional anisotropy, which is increased in white matter regions with dense parallel white matter fiber bundles. The mean diffusivity, which is modulated by the density of the tissue. The major eigenvector direction, often assumed to be parallel to the white matter tracks and may be represented using color. In addition, the parallel and perpendicular diffusivities provide information about the white matter microstructure. To review, the three eigenvalues, lambda 1, lambda 2, and lambda 3, ranked from largest to smallest, provide information in white matter about axonal degeneration and myelination. The average is the mean diffusivity, which is sensitive to the density of the tissue. The major or largest eigenvalue is sometimes referred to as the axial diffusivity, or AD, and is often assumed to be parallel to the white matter tracks. The average of the medium and minor eigenvalues is called the radial diffusivity, or RD, and is assumed to be perpendicular to the white matter and appears to be modulated by white matter myelination. Here is an example of DTI axial and radial diffusivity measurements in an animal model of dysmyelination. The measurements on the right corresponding to the dysmyelinated animals show increased radial diffusivities of white matter, which is associated with less myelination. The corresponding axial diffusivities do not appear to be affected. Another widely used DTI measure is the fractional anisotropy, or FA. It ranges from 0 to 1 and is greatest in regions of white matter with highly parallel compact axonal bundles, such as the corpus callosum and the cortical spinal tract. One important factor to consider is the signal-to-noise ratio, or SNR, of the diffusion-weighted images. Low signal-to-noise ratio studies will cause the eigenvalues to be biased with increased measurement variance, as shown by the plots here. For the isotropic case on the left, the eigenvalue should be equal, but one eigenvalue is overestimated while another is underestimated. This will lead to an overestimation of FA in regions with isotropic diffusion. The plot on the right also shows that the medium and minor eigenvalues are biased in a region of highly anisotropic diffusion. As mentioned, the biasing of the eigenvalues for low SNR measurements will lead to biased FA estimates, and this bias will be more pronounced for low anisotropy measurements. These plots illustrate this FA bias phenomenon for low signal-to-noise ratios. It should be noted that this SNR bias is less likely to be for most modern DTI protocols with large numbers of encoding directions and modest resolution on the order of 2 millimeters or more. However, as protocols acquire data with 1.5 millimeters or less, having long echo times greater than 80 milliseconds or poor coil sensitivity, like in the brainstem and spinal cord, the potential bias from low SNR should be considered. Another issue is that DTI measurements across sites and scanners can be highly consistent. Here is an example of reported DTI measurements up to 2004 and the GNU of the corpus callosum as being highly variable. Fortunately, DTI measurements across scanners today are more consistent, but intersite variability is still an important factor that must be accounted for in multi-site studies. If you plan to do multi-site DTI or brain imaging in general, I would strongly encourage that you investigate methods for harmonizing the data. The variation in local white matter organization across the brain, such as regions of crossing and divergent white matter fiber tracts, ultimately leads to really broad ranges of FA values in white matter, which presents challenges in reporting and interpreting FA values of white matter. Here we're showing the range of FA values for supposedly healthy white matter, ranging from roughly 0.15 all the way up to 0.9. A range of pathologies in white matter can also influence FA, thus the pathological specificity may be quite poor. Here are several examples of different white matter pathologies that will decrease the FA. They include demyelination, axonal loss, vasogenic edema, and cellular infiltration. Often pathology can include a mixture of these processes. Consequently, a reasonable question is to ask why use DTI if it is not very specific. The answer is that it is extremely sensitive to microstructural changes from a broad range of factors as listed here, as well as others. The application of DTI is going to be most powerful when used to study specific processes and/or pathologies where specific mechanisms may be known a priori.